Whatever the instruction we are going to provide, that is in the form of commands. Whatever the extended binary coded decimal interchange code we are having that contains 8 bits. What is ASCII here? That is nothing but American Standard Code for Information Interchange. Hello to all, a warm welcome to my new session on data representation. I'm Revati, faculty, Department of Computer Science, Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. Before going to start my today's session, let me to recall the things what we discussed in my previous session. In my previous session, we started with subtraction of binary numbers using complements. So, to represent positive numbers, I'm having number system. That is nothing but I'm having binary number system, octal number system, decimal number system, as well as hexadecimal number system. But if I consider negative numbers, to represent negative numbers in computers, we don't have any number system. For that, we are having ones complement method as well as twos complement methods. That means to represent negative numbers, I'm having ones complement method and twos complement method. So what is ones complement method here? Whatever the binary number I'm having, I'm going to write the inverse of that. For example, if I'm having 0, what I will do, I'm going to make it 1. If I'm having 1, how I'm going to write? I'm going to write it as 0. And what about 2's complement? First, I need to take the ones complement of a given number. Then I want to add 1 to the LSB bit. So that is nothing but the 2's complement method. In my last session, we had two different types of subtraction, that is subtraction using ones complement method and subtraction using twos complement method. Then we had discussion regarding the second type, that is subtraction using twos complement. Here also, once again, I'm having two cases, that is the magnitude is greater than subtrahend, and the second case here is magnitude is less than subtrahend. Then we had discussion regarding second type, that is subtraction using twos complement method. Under subtraction using twos complement method, we are having two possibilities. One is the magnitude is greater than subtrahend, and the second possibility is the magnitude is lesser than subtrahend. Then we had discussion regarding how to solve these kind of cases along with the steps. So these are the certain topics we learned in my previous session. But in today's session, we are going to study about computer codes. So what is computer code? What is the necessity of computer code? How the computer is able to understand computer code? Along with that, we are going to study the different types of computer codes which is supported by the computer system. Then what are the different types of computer codes are understood by the computer? That is nothing but BCD, Xs3, then EBCDIC, along with that ASCII. Anyway, we are going to study all these topics in depth. Instead of wasting much of time here, directly dive into the today's session, that is computer codes. So if I consider computer system, computers are able to understand only instruction, and whatever the instruction we are going to provide, that is in the form of commands. And The computers are able to understand only machine language. So here computer code helps us to represent the character in a coded form in the memory of the computer. Dear student, why I required computer code here? I required computer code to represent the characters in a coded form in the computer memory. For example, say if I press A, now this A is converted into some form and that is stored in the computer memory because computer understands only zeros and ones. Now tell me what is this 0 and 1? Here 0 is nothing but low or off or false value. And if I consider 1, it is nothing but true or on and high value. So dear student, just remember that the computer understands only binary code. There's nothing but the machine code. And whatever the data we are going to read from the keyboard, that must be represented in some coded form. After representing that in the form of computer codes, that is stored in the computer memory. So these codes represent specific format. So dear student, just remember here, whatever the computer code we are having, that represents some specific format in which the data are recorded. And the most commonly used computer codes are binary coded decimal. It is called BCD. And we are having extended binary coded decimal interchange code. I repeat, the second type is extended binary coded decimal interchange code. And we are having ASCII code. That's nothing but American Standard Code for Information Interchange. Along with that, we are having Xs3 Code. And these three types are weighted number system. And this is example for non-weighted number system. And this is very, very important topic because you can expect these topics for 1 mark. That is nothing but you're going to expect the question like write the abbreviation of BCD or expand extended, that is EBCDIC or expand ASCII. In that time, you need to write the abbreviation of all these short forms. So here, what is BCD? BCD is nothing but binary coded decimal number system. Or I'm having EBCDIC, that is extended binary coded decimal interchange code, and I'm having ASCII. Here ASCII is nothing but American Standard Code for Information Interchange, and all these are example for weighted number system. Now I'm having BCD code. So what is BCD code? In my previous session, we had discussion regarding number system. So in number system, we are having 8-4-2-1 form. That means to represent binary numbers, I'm going to follow this method. So this is nothing but binary coded decimal, or it is also called weighted number system, or it is also called 8-4-2-1 code. So here, what is BCD? Here BCD stands for binary coded decimal. That means whatever the decimal number I'm having, I'm going to represent that number in the form of binary. And if I consider decimal number system, I'm having 10 digit and it starts from 0 to 9. And if I consider binary number system, I'm having only 2 digits, that is nothing but 0 and 1. And to represent decimal numbers, I'm going to follow this way, that is nothing but 8, 4, 2, 1. So here 8, 4, 2, 1 is nothing but the weight. This coding system, the bits are given from left to right. So, while representing the weight, I'm going to start from left to right. So, at the beginning, I'm going to write 8, then I'm going to write 4, then I'm going to write 2, and I'm going to write 1. So, that is nothing but 8, 4, 2, 1 respectively. Now, consider the example that I want to represent this 5 in the form of BCD. Now, how can I form by using 8, 4, 2, 1? That's nothing but by adding 4 and 1, I can able to get 5. So, what I will do? I'm going to write in place of 1, 1, and in place of 4, I'll write 1. And in the remaining position, I'll write 0 and 0. So, this is the BCD representation of given decimal number 5. Dear student, just think that I'm going to have decimal number 12. Now, I need to represent this decimal number in the form of 8421. To represent 12, I'm going to consider this BCD code. So, if I add 8 plus 4, I'm going to get 12. So, what I will do here? I'm going to write in front of 8, 1, and I'm going to write 1 in front of 4. And I'm going to place 0 and 0 in place of 2 and 1. This is the way I can able to convert the decimal number into binary. Now I'm having the table and it gives the BCD representation. That means I'm having decimal number, and how can I convert that decimal number to BCD? So here at the beginning I'm having 0. To represent 0, I'm having 4 zeros, because what is BCD? It is nothing but the position of the given number. 8, 4, 2, 1. How many positions I'm having? 4 positions or 4 bit. So, to represent 0, I'm going to write 4 zeros. Now, consider another example that I'm having decimal number 6. Now, I want to convert this number to BCD, or I want to represent this decimal number to BCD. How can I? While adding 4 plus 2, I'm going to get 6. So, what I will do? I'm going to place 1 in front of 4 and 2, and remaining place I'll write 0. If I consider this table, to represent 6, I'm having 0, 1, 1 and 0. And if I consider another example, say I want to represent 15 in the form of BCD. Now, if I consider 8, 4, 2, 1. Now, if I add 8 plus 4, it is 12. 12 plus 2, it is 14. 14 plus 1, it is 15. To represent 15 in my BCD, I want to consider all 4 positions. So, what I will do? I'll write 1, 1, 1 and 1. This is the way I can able to represent my decimal number 15 to 4, 1 in my BCD representation. Moving further, I'm having some example here. So, what's the example I'm having here? That is 537. To represent this number, first what I will do? I'm going to break this number into individual digit. After that, what I will do? I'm going to write the BCD representation for individual digit. So first I'll consider 5 and I'm going to write the BCD representation, that is 0, 1, 0, 1. That's nothing but 5. And for 3, it is once again 0, 1, 1, 0. And if I consider 7, it is 0, 1, 1. And it is binary coded decimal representation. So I need to consider 4-bit because here we are having 8, 4, 2, 1. And at the end, what I will do, I'm going to club all the result together to get my final result. So here I'm having some disadvantage. What is the disadvantage here? By using BCD number system, I can able to represent only 2 to the power 4. That is nothing but 16 characters. So here by using BCD, I can able to represent only 16 characters and it is insufficient to represent all the characters. So what is the solution here? For that, we are having 2 to the power 6. That is nothing but I can able to represent 64 character. That is nothing but 2 into 2 into 2 into 2 into 2. That is nothing but 64. Initially, we can able to represent only 16 characters. After modifying that, we can able to represent 64 character. Now, if I consider 2 to the power 6, then what's the possible value I can able to have here? That is 1, 2, 4, 8, 16 and 32. Now think that I'm having example 21. Now I want to represent this decimal number 21 in the form of BCD. How can I? See here, I'm having 2 to the power 6, that is 32, 16, 8, 4, 2, 1. If I consider here by adding 16 plus 4 plus 1, I'm going to get 21. So what I will do? In place of 16, I'll write 1. In place of 4, I'll write 1. And in place of 1, I'll write 1. And for rest of the weight, I'll write 0, 0, 0. So this is the binary representation of given decimal number. So this is the way I can able to convert or represent the decimal number to BCD. Now I'm having another type, that is nothing but Xs3 code. Now here we are going to study how we can able to represent the given data in the form of Xs3. As the name itself indicates that whatever the data we are having, for that we are going to add extra 3 value or extra 3 weight. So here if I get 5 plus 3, how much it is? 8. To represent this, I'm going to have Xs3 binary coded decimal code. That is nothing but first I want to write the binary representation of given digit or decimal number. So what I will do, first I'm going to write the binary number here, that is 0, 1, 0 is nothing but 5. Then what about 3? How can I represent 3 here? That is 0, 0, 1, 1. Now what I want to do? I want to add 5 plus 3. Then what I want to get? I want to get 8. So here I'll write 0, 1, 0, 1, 0, 0, 1, 1. Now I'm going to perform binary addition. So 1 plus 1, I'm going to get the sum 0. 1 is carry. 1 is carry. So now what I will do, I'll add 1 plus 0 plus 1, that is 1, 0. So what I will do, I'll place 0 here, 1 is carry. Now 0 plus 1, it is 1, 1 plus 1, it is 0 and 1 is carry. So 0 plus 0, it is 0, 0 plus 1, it is 1. So it is nothing but 8. This is the way I can able to represent the given decimal number into Xs3 form. So the Xs3, there is nothing but Bcd coded is non-weighted. That means to convert this Xs3, I'm not going to follow any weights. So this is the example for non-weighted number system. So the Xs3 Bcd codes are represented in the form of non-weighted codes. That means I'm just going to add 3 to the given decimal number. The name Xs3 code is derived from the fact that each binary code is corresponding Bcd code plus I'm going to add 3. So here, if I consider any decimal number, first I want to convert that into the Bcd. After that, I want to add the decimal number 3 for that. I cannot add decimal number 3 directly. So what I want to do, I want to take the binary representation of decimal number 3 and I want to add that with the Bcd code. This code is used in some old computers. Now the question arises where we can able to use Xs3 codes, because nowadays we are not going to use Xs3 codes, but these codes are used by some old computers, and the following table gives the complete information about the Xs3 codes. So dear student, just remember here, if I consider Bcd, that is example for weighted. That means we are going to consider the position, and how many positions we are having? Only 4. And if I consider Xs3, then here we are not going to bother about the position. That means we are not going to concern about the position of given number. Dear student, if I consider Bcd, that is the example for weighted code. That means for each bit, we are going to write the weight, or we are going to consider the position of the bit. But if I consider Xs3, then here I'm going to convert that decimal number to Bcd and I'm going to add 3. That's it. So here I'm having 3. This is the binary representation of 3. Then what I want to do? I want to add plus 3. So 3 plus 3, it is 6. Then how can I represent 6? That is 0, 1, 1, 0. That means first I'm going to take 3. To represent 3, I'm having 0, 0, 1, 1. Then I want to add 3, that is 0, 0, 1, 1. Now 1 plus 1, sum is 0, 1 is carry. Now 1 plus 1, it is 1, 0, plus 1, it is 1, 1. So I'll write 1 here and 1 is carry. I'll write it here. Now 0 plus 0, it is 0. So this is the Xs3 representation of given 3. And if I consider 9, how can I represent 9? That is 1, 0, 0, 1. Then what I want to do? I want to add plus 3. So what I'm going to get? I'm going to get the result 1, 1, 0, 0. So what I will do here? I'm going to write the binary representation of 3 and I'm going to perform addition operation. Now I'm having 1 plus 1, it is 0 and 1 is carry. 1 plus 0, it is 1, and 1 plus 1, it is 0 and 1 carry. Now at the end I am having 0 plus 1, it is 1. So 1100 is nothing but the binary representation of given decimal number 12. This is the way I can able to convert the BCD number to Xs3 numbers. Now I'm having the example here. See, I'm having 5. Now I want to convert this 5 to Xs3. So what I will do? I'll add plus 3 here. 5 plus 3, it is 8. So here I'm having 1, 0, 0, 0. And if I consider 3, I want to add 3. So 3 plus 3, it is 6. So to represent 6, I'm having 0, 1, 1, 0. And here I'm having 7. First, I want to write the binary representation, that is nothing but Bcd code. Then I'm going to add 3 here, that is nothing but 0, 0, 1, 1. And I'm going to perform addition operation, that is 1 plus 1. I'm going to get the sum 0 and 1 is carry. So here 1 plus 1, it is 1, 0. Plus 1, I'm having 1, 1. So my sum is 1 and carry is 1. Now I'm having 0 plus 1, it is 1. And when I add 1 with the carry, I'm having 0 and 1 is carry. So 0 plus 0, it is 0. 0 plus 1, it is 1. So it is nothing but the 10. So this is the way I can able to represent BCD to Xs3. So dear student, just remember here to represent BCD to Xs3, I just want to add decimal number 3. First, I want to convert that to binary, then add that to BCD. This is the way I can able to convert BCD to Xs3. Then I'm having EBCDIC. This is the one of the important topic and you can expect for 1 mark. So what is EBCDIC? So here EBCDIC is nothing but extended. The name itself indicates that it is extended binary coded decimal interchange code. This is the extension of BCD. That means by using BCD, I can able to represent 2 to the power 4. That is nothing but 16 character. To overcome this, we are having 2 to the power 6. That is nothing but 64. That means I can able to represent 64 character. But still BCD is going to have the disadvantage. That means if I'm having larger character set, and how can I represent? For that reason, we are having extended binary coded decimal interchange code. To represent this, we are having 2 to the power 8. That is nothing but I can able to represent 256 different characters by using EBCDIC. That is nothing but binary coded decimal interchange code. So it was developed by IBM. That is nothing but International Business Machine, and it uses 8-bit code to represent 256 different characters, and it is used by the most of the computers as well as most of the computer equipment. For that reason, the most commonly used number system is extended binary coded decimal interchange code, and it is most frequently used by the computers, that is nothing but mainframe computers, to represent letters, numbers and symbols in a binary language the computer can understand. Because computer understands only machine language. So here machine language is nothing but zeros and ones. It is also called binary language or binary code. Here computer understands only binary code to represent characters, numbers and symbols. We are going to use extended binary coded decimal interchange code. So here the extended binary coded decimal interchange code is an 8-bit code. Therefore, it is divided into 2-4 group. That means to represent 2 to the power 8, I'm having 8 bits. So what I will do here, I'm going to divide 8-bit into 2 different 4-bit group. That means I'm having 2 groups and each group includes 4 bits. That is nothing but here the extended binary coded decimal interchange code is an 8-bit code. Therefore, it is divided into 2 4-bit groups where each 4-bit can be represented as 1 hexadecimal numbers. That means whatever the extended binary coded decimal interchange code we are having that contains 8 bits. So what I will do, I'm going to divide this 8 by 2. So I'll make 2 groups and each group includes 4 bits and it is used to represent 1 hexadecimal digit. So dear student, from the examination point, this is also very important topic. And the last topic under this chapter is ASCII. So what is ASCII? Why we required ASCII? This is also one of the important topic and you can expect 1 mark question. That is the abbreviation of ASCII. So what is ASCII here? That is nothing but American Standard Code for Information Interchange. Here computer understands only machine code, that is nothing but binary code. Now whatever the data or whatever the character we are having, we want to convert that to machine understandable form. For that we are having computer code. In computer code we are having BCD, Xs3, then extended BCD. Along with that we are having ASCII, and ASCII, BCD and extended BCs are example for weighted codes and Xs3 is example for non-weighted codes. That means to represent character, we are not going to consider any position or weight of the digit. But if I consider rest of the codes, then to represent the digit or to represent the bit, we are going to consider the weight. For that reason, it is called weighted code. So, it is nothing but 7-bit code. So, what is ASCII here? That is nothing but 7-bit code. That's nothing but 2 to the power 7. That means I can able to represent 128 characters. That is nothing but 0 to 127 character, and it is used in most of the microcomputers and mini computers. So dear student, where this ASCII codes are used, this is used by most of the mini computers as well as microcomputers and mainframe computers. Now the question arises, how the computer understands ASCII code. Now, if I want to interact with the computer, I want to provide the commands or instruction. And whatever the commands I'm going to provide through the keyboard, that must be understood by the computer. For example, if I press A, letter A from the keyboard, the computer understands this is A by using ASCII code. That means whatever the letter I'm going to press, that is converted into ASCII form. Then only the computers are able to understand this is the letter. And in ASCII, for each letters, numbers, and for special characters, we are having ASCII representation. So, the ASCII code that is pronounced as Ascii is of two types, that is ASCII 7 and ASCII 8. That means by using 7-bit, I can able to represent only 28 characters. If I use ASCII 8, by using ASCII 8, I can able to represent 256 characters. So, ASCII 7 is 7-bit code used to represent English characters as numbers. That means whatever the character or whatever the number I'm going to press, that is converted into ASCII. For example, if I consider capital letter A, then what's the ASCII code for A? It is 65. And if I consider Z, then it is 90. And if I consider small letter A, then it is 97, and Z, it is 122. And in computers, both the uppercase and lowercase letters are different. For that reason, the range of the ASCII is also vary. So here, for capital letter A, it is 65. And if I consider small letter A, it is 97. And if I consider numbers, to represent numbers, we are having ASCII value. To represent special characters, once again, we are having ASCII value. For example, think that I'm having capital letter M. That means I'm going to press capital letter M. That is converted into 7 because computer understands only machine language or binary code, and to convert the character to machine code or binary code, we are going to use computer codes. In that, we are going to use ASCII code. So, dear student, in this chapter, we started with what is number system. Along with that, the two type of number system, that is positional number system, non-positional number system. Along with that, we had discussion regarding how to convert one number system to another number system. Along with that, we had discussion regarding how to represent positive numbers and how to represent negative numbers. Along with that, we had discussion regarding ones complement method as well as twos complement method and how I can able to perform the addition. Along with that, we had discussion regarding computer codes. In that, we discussed what is BCD, what is Xs3, and what is extended BCD, and what is ASCII. Dear student, from the examination point of view, this chapter is very important, and you can able to expect 11 marks from this chapter. So, dear student, let's meet in the next session with new topics. Until then, keep learning and keep watching. Thank you.